Hi everyone, welcome to VSAONLINE. So it's 8 p.m. GMT and we begin our webinar. So today it's my pleasure to host Hussam Amrouch from TU Munich. So without any further delay, Hussam, the floor is yours, or the screen is yours.
Okay, thanks a lot for having me here. So today I'm going to share with you about hyperdimensional computing, but from more hardware perspective, how we can really design a friendly hardware software co-design for the best use of the hyperdimensional computing with a nice synergy between the hyperdimensional computing and the in-memory computing. In this talk, it would be kind of a journey that I would like to take you from the beyond CMOS technology and emerging technologies to beyond traditional deep learning, where the hardware software co-design for hyperdimensional computing, and precisely how we can have the nice synergy to build a reliable algorithm from HDC on top of unreliable technologies like the emerging beyond CMOS technologies. And this journey would not be complete without we stop in between for novel and beyond traditional von Neumann architectures, where we can think about how we can have novel circuit designs to realize the best of the beyond CMOS technology with the beyond deep learning algorithm. There is no doubt that the next revolution of humankind is coming from AI. And if we look to the many of the breakthroughs in AI nowadays, we notice that this would not be possible without the tremendous increase in the computing demand. This data that has been analyzed from the large language models or many of the large models that released in the recent years, the data suggests that the computing demand of deep learning algorithms is doubling tremendously. Almost every 3 to 4 months, the computing demand is doubling. And if we think about it, this would not be possible, such breakthroughs and such complex AI models would not be possible without breakthroughs in the underlying hardware. In fact, because the efficiency of the underlying hardware has increased tremendously in the past few years, the AI algorithms start to become more powerful. And this all happened and started when specialized hardware has been proposed. And for instance, a few years ago, when Google announced the Google TPU, the tensor processing unit, which was the first domain-specific AI chip, the complex deep learning algorithms start to be trained by merely few minutes compared to what we would need traditionally more than 2,000 GPUs and 500 CPUs. And this was possible on one complex AI chip. Now, efficiency, the large increase in the efficiency of the hardware actually opened the door for all those AI models to become larger and larger. But we might actually ask ourselves if efficiency is always good. And it's really having more and more efficient hardware is always good. If we go back to the previous revolution for the humankind, and we go back to the Industrial Revolution in 1865, when Jevons from England, he observed that after the invention of the steam engine, which was by far much more efficient engine compared to any other engine back then, the total consumption of coal was keep increasing instead of decreasing. How could it be when the technology makes process much more efficient? We don't have saving. Years later, this became to known in economy as Jevons paradox. Whenever the technology increases the efficiency, the consumption rises. And most of the gain of the efficiency or from the efficiency will be compensated, if not canceled out, and too much efficiency might even backfire. How this is really related to our topic and AI, if we think about it, because of the hardware became by far much more efficient, and because we could produce efficient hardware that can train AI models much faster and more efficient, the AI models start to become bigger and bigger and larger. And this is quickly start to put us in front of the fundamental bottleneck in our existing computer architecture, the fundamental bottleneck in von Neumann architecture, which is coming from the memory wall. And therefore, lots of efficiency, significant efficiency losses start to happen. And at the end of the day, most of the efficiency that we are gaining from our hardware and in the presence of those large models start to become really problematic. And most of the efficiency that we wanted or we hoped was lost at the end of the day. And this is kind of a manifestation of Jevons paradox instead of economy, but maybe in hardware and AI. To solve this problem, novel architectures in which we overcome the fundamental bottleneck in memory becomes a must. And if we ask ourselves about the reason about that, what the roots behind those energy crises that most of the AI hardware, if not all the AI hardware, really suffer from, we can really trace it back to two major factors. First and foremost, if we look to any of those AI hardware accelerators, the architecture is quite straightforward. We have many multiplications, like in this case, a systolic array that consists of 64,000, so a very large array to do multiplications, to accelerate the array multiplications, the matrix multiplications, and such a 64,000 multiplications happening in parallel in a very small area where we know that multiplications are very, very power hungry. Very quickly, we will get a high power density, and as a result, we will get a very excessive heat where expensive cooling becomes necessary. On the other side, we see that despite the fact that 29 or 30% of the chip in this example from Google TPU has been reserved for the memory, for the on-chip memory, the total memory that we get here is merely 24 megabyte, which is, we know it's literally joke or nothing when it comes to large language models or any large decent deep learning model. And because the inefficient chip memory, which is an inherent problem in the existing technology, we have a massive data to be moved between the compute engine, the systolic array, and the off-chip memory. And this will put us again in front of the von Neumann architecture, the bottleneck, the fundamental bottleneck there. And that causes lots of energy consumption because the data movement is extremely expensive. So both of them, the expensive cooling that's coming from the fact that we have many expensive heavy computations attributed to the multiplications, thousands of them happening at the same time within a small confined area. So this expensive cooling together with the expensive data movement due to the von Neumann bottleneck, those are responsible largely to the energy crisis that AI hardware suffers from. But we might even ask ourselves a more fundamental question: what is really the root behind those problems? First and foremost, the voltage is reaching its fundamental limit. We, of course, heard in the last 10 to 15 years that voltage scaling is slowing down, but actually in technology, we are almost at the fundamental limit in voltage scaling. In fact, the voltage scaling is attributed to the subthreshold swing, the fundamental limit there, which is 60 millivolt per decade. And if we look to the technology from TSMC and other vendors, already a few years ago, they reached around 64 millivolt per decade, which is extremely close to fundamental limit. On top of that, the existing CMOS technology to build memory using SRAM is inherently inefficient. So we need more than 6 transistors to store a single bit. And as we have just seen in the previous slide, that despite the fact we reserve 30% of the chip, we can only accommodate 20 to 24 megabyte, which is not really considerable or very small when it comes to any decent deep learning model. Finally, cooling is inherently inefficient because we still cool down the entire chip, despite the fact that the hotspot is localized on one small area in the chip where the computation is happening, and the existing cooling is inherently inefficient. So therefore, we cannot tolerate all these heavy computations that's happening. And all those factors together and all those walls and those limitations, they really put us in front of the end of the line. As David Peterson, the pioneer in RISC architecture, he used to say that we are, when it comes to the single thread performance, we are literally at the end of the line. And unfortunately, this is happening at the same point of time in history where the need for computing demand, the need for more and more computing demand is increasing and doubling every 3 to 4 months, as we have seen at the beginning of the presentation. So therefore, if we think about the recipe, where the innovations needs to happen, In fact, we need a very cross-layer innovation, starting from the deep in the technology, where we'll figure out different beyond CMOS technology, coupled with different way to do the computations, to do something like beyond traditional von Neumann, where we can really merge the memory and the computation together to do in-memory computing, eliminating the need for any expensive data movement. And when it comes to emerging technology, that's by definition immature compared to CMOS technology. And when we really couple that to analog computing or any computing that goes beyond traditional computing, traditional von Neumann computing, errors becomes absolutely inevitable. And when we have errors, we need that we think beyond deep learning algorithms, because deep learning algorithms are not good in tolerating errors. And here it comes to play the hyperdimensional computing due to its great robustness against errors, as we will talk soon in great detail. And finally, if we really want to do the combine emerging technologies and emerging architectures and put them on top of non-traditional machine learning algorithms like hyperdimensional computing, hardware software co-design becomes a key to achieve reliable computing, reliable machine learning on top of those unreliable hardware and unreliable components. And I will start this journey by motivating you. Where is the problem in our existing technology? You heard about that 5 nanometer from many vendors or from the key vendors already in place. The 3 nanometer is coming to the mass production pretty much soon in the next year. So where is the problem in the existing technology? Well, the key problem in the existing technology, it comes from the fact that the voltage, as I just mentioned, is not really scaling down. At the same time, the geometry becomes smaller and smaller. And this leads quickly to fundamental problem in reliability in the technology, attributed to the so-called self-heating in transistors, where the generated heat inside the transistor is trapped inside and cannot escape to outside. Many examples, and this is the analysis we have done in our research for advanced FinFET technology, nanosheets, which is the next generation, along with the nanowires, we can see always that reliability is a big concern there, because the extreme 3D confined structure coupled with the high voltage where self-heating becomes a real killer for the reliability. So therefore, advanced technologies and just making the technology better and better, it comes with the cost as reliability becomes lesser and lesser. And reliability, when it becomes worse, this manifests itself quickly as errors in the system level. So therefore, we have always to challenge ourselves and question, do our traditional deep learning algorithms work well with errors? And those errors are inevitable if we keep doing our technology scaling, or even worse, if we change our technology and adopt an emerging technology. So therefore, we have to always question about the robustness of our machine learning algorithms against errors. It's not like a nice feature, but it becomes more and more a must in the near future. And here it brings me to the emerging technologies. And I will talk in particular about the non-volatile memory, because as you remember in the beginning of the slides, we attributed most of the problems that we have to the insufficient on-chip memory that's coming due to the area hungry that SRAM, traditional SRAM CMOS really necessitate. And here I'm going to share with you and talk about one of the emerging technologies. It's called ferroelectric FET, ferroelectric transistors. And this can be realized from the traditional CMOS by replacing the traditional high-K material with a ferroelectric material. Without going into too much details, I just want to give you a feeling that this ferroelectric technology, it's exactly the traditional CMOS technology, but we change the material of the gate with a different material. What that really means, it means that this technology is very close to what we used to work with, what we used to understand, and what we used to produce for many decades. Therefore, the chance to be adopted by the industry is quite high, because the cost for adaptation becomes much less, and the physics behind it is straightforward. Now, this ferroelectric contains dipoles, and these can be polarized either up or down based on the direction of the electric field. So if you apply positive voltage, for instance, you can polarize the dipoles or polarize the ferroelectric into a certain direction. Let's say it's up. And if you apply a negative voltage, you polarize in the opposite direction, let's say down. And this can be vice versa. This is just an example. But whenever you have such additional polarization in the transistor, this actually separates the transistor into two different distinguished states. We call them low VT state and high VT state, or in other words, low current and high current. As this picture indicates, you have now the same transistor, but based on the stored polarization, it can provide you with a high voltage or high current or low current. And this is a realization of a memory, because now the transistor can store information stored in the sense of the polarization that's inherently stored exists there. And then when we want to read from the transistor, we get either high current or low current, which will allow us to interpret it as logic 0 or logic 1. So very simple, but extremely powerful, because now for the first time, we are able to realize an ultra-dense memory. A single transistor can store information, and more importantly, is ultra-low power because it's driven by electric field, not by current. And finally, and the most important feature, it's fully compatible with the existing CMOS. So therefore, it can be easily integrated with the fabrication process. And more importantly, we can really tape out and design circuits that have traditional CMOS and emerging ferroelectric side by side on the same die, which is very important. And now, if very quickly we imagine, if we go to this hardware accelerator, where a third of the chip traditionally, conventionally, used to be reserved for the on-chip memory. And now if we just replace it by a ferroelectric memory where we are able to store every bit with a single transistor, then you can imagine quickly how the memory footprint and the capacity increases largely, which will eliminate largely the data movement and the DRAM communications, which is responsible for lots of the energy consumption of those AI hardware processors. Now, from this single transistor, from this single transistor memory, I want to go and walk through with you how we can build a small cell to do an in-memory computing. The concept is quite simple. Now let's remember that based on the polarization, based on the voltage that you apply to the transistor, you can actually make the transistor to be either high current or low current, either blue or red in this analogy. And now, if we take two of those transistors, only two, and just connect them in this shape that you see it here, and we can build it like a cell, and we have those transistors connected to each other. And whenever we store information inside this cell, I would call it, let's say we store 0, then we always store it in a complementary manner. What that really means, one transistor, we put it in high current mode, and one transistor, we put it in a low current mode. One in the blue, one in red in this example. So always whenever we store information, we store it in a complementary manner. So far, so good. Then we apply an input to this cell, and this SL here line, it refers to search. So now we want to search. We want to apply a certain input, and let's assume here I'm applying 1. And because I'm applying 1, what will happen, the blue transistor will start to conduct. And because of the conducting path, what we will get now, we will get a discharge. We have a current. And therefore, the high VDD will go down to the ground and we get 0. So that means now if I store 0 and apply 1, I will get 0. So what happens now if I do the opposite? If I store 0 and I apply 0, the post transistor remains off and I don't have any conducting path. So therefore, the VDD voltage that we apply on top remains high. In other words, we have no conducting path, there's no discharge. And if I have stored 0 and I apply 0, I get 1. In other words, I'm able, based on sensing the current, to figure out if I have a match or mismatch. If I have mismatch, I will get 0. And if I have match, I will get 1. But what that really means, in Boolean language, it means an XOR operation, or XNOR operation. Sorry, there's a type on XNOR operation. And that means like if I have 1, 1 or 0, 0, I will get 1. And if I have 1, 0 or 0, 1, I will get actually 0. And from that logic in memory, I can build now a nice architecture that allows me to do an XNOR operation without accessing the data. And let's remember that such operation is important because it can tell me quickly about the similarity. Now let's move from that single cell to an architecture. And we will see now how we can do a more complex Boolean function using beyond von Neumann architecture. So if I take this cell that I have just explained to you, and if I just put multiple of them in one array, and then if I go and I store information, a certain vector, let's say 1, 1, 0. Now, if I search for another vector, and let's say 1, 0, 1, what we will get actually in this example that we have two cells, we will have mismatch, and therefore they will have a conducting path, and the third cell will have match, and will not conduct any current. Now, if I really sense the current that I'm getting from this array, I can quickly interpret the number of mismatches that happen, and in other words, I can calculate the Hamming distance. That is awesome because we know that Hamming distance, again, can tell us quickly about the similarity between two vectors. And now, for the first time, instead of I do complex arithmetic calculations or operations in the CPU in order to calculate the Hamming distance between two vectors, I'm able now to do a Hamming distance calculation between a vector that's stored in the memory and then directly apply another vector and sense the current in an analog fashion and interpret it to the Hamming distance calculation. You can easily imagine lots of saving happening. You don't need to read from the memory. You don't really need to do complex logic function. You don't need even to do an addition. You have now only the Kirchhoff's law where all the currents will be summed up naturally from physics. And then you take that current, you apply very simple sensing circuit where you can really compare the current to some reference current, and then you can interpret the results to the Hamming distance. Well, that means lots of saving, and we were able to do Hamming distance computation inside the memory itself. And this is an example where you can see the discharge rate or the current from the Hamming distance, and we can see how at the very different points of time, if we sample it, we can really figure out, or we can interpret whether how many bits or what is really the Hamming distance. Now, when we talk about Hamming distance and when we talk about this nice in-memory computations, now we should think about, we need different algorithms, different than traditional deep learning, where it can make the best use of this novel architecture. And here, hyperdimensional computing becomes really interesting and a very interesting example. And if you wonder why hyperdimensional computing is anyway interesting, despite the synergy of the in-memory computing, which I'm going to explain in the next few slides, we should remember that deep learning, despite if it's on the data centers or on the mobile devices or on the edge, inherently power hungry. Deep learning relies on complex and expensive math operations, multiplications, and accumulations. It needs large arrays to really ensure large matrix multiplications to be done in parallel in an efficient manner. And despite if we talk about 32-bit floating points, and even if we quantize it to 8-bit integer, still these architectures or these algorithms inherently data hungry. So therefore, deep learning algorithms is by definition data hungry and power hungry. So therefore, whenever we want to think about algorithms that can save more energy, either we have to quantize deep learning severely to 2 bits or even 1 bit, where accuracy would be compromised quickly, or we have to think about the replacement of the deep learning algorithm. And this is where hyperdimensional computing holds a promise. And this is an analysis that we have done it for the power density for traditional deep learning algorithm. We have an example of systolic array of 128 by 128, which is something reasonable for complex AI algorithms or deep learning algorithms, or maybe on the data centers. We see how the power density can easily go to above 200 watt per square centimeter, which can be interpreted or cause an excessive temperature that reach above 125 degrees. And that explains the biggest challenge in deep learning algorithm when it comes to power, to temperature, due to the inherent complex operations. So therefore, alternatives to deep learning algorithm becomes really a must if we want to really think about something very efficient and more suitable for even edge computing. And here, hyperdimensional computing, and I know most, if not all, of the audience online, and I'm sure, I'm very confident that everyone also here in the session, extremely confident, extremely familiar with the hyperdimensional computing. So I will go with the basic, really, example about the binary hyperdimensional computing, and I will really borrow the example of Penty, which is he's here. So I'm very happy to see that he's here listening to the talk. And we can take this traditional example of the language classifications, where we take the characters in the language, so let's say A, B, C, etc., and we assign large random bits vector. How large? Well, something like in the area or on the size of 1,000 bits to 10,000 bits, for example. And then if you assign those random bits, and because they are completely random, so the chance to have any similarity becomes very small. And then we will apply a very simple algorithm, and without going into too much technical details, I want to give you a feeling that this algorithm is extremely simple, relies on rotation and XOR operation. So not really something complex where MAC operations happening in deep learning. So we apply this encoding scheme, and we call it for n-gram, and n can be a number such as a 3. And if you go to traditional text like to be or not to be, and you want to do the training, then actually you take those 3 characters and you start to apply these simple operations and XOR and rotate, and you continue that, and every time you get a new vector where the information keep encoded, be encoded and encoded, and finally we apply very simple majority vote, and we end up like a new vector. So again, I don't want, or my goal is not really to explain the algorithm in great detail. The algorithm is quite simple, and there's many fantastic talks in YouTube that explain how the algorithm works. But my goal now to give you very simple and quick feeling about the simplicity of this algorithm, where you quickly can realize that compared to any deep learning algorithm, this is by far much simpler, especially in training, where the biggest improvement. Now, the entire language in this example can be encoded in one hypervector, and if you apply the same algorithm for different languages, let's say Italian, French, etc., then every time you end up by a new vector, and that vector kind of encodes the information and in that language. Now, if we go back to our example that we talked about, the memory array from those XOR elements, which is in principle, by the way, I forgot to mention that those are like a kind of CAM, content addressable memories, because you store information and then you just check if this information exists or not. So if you take those vectors that you already trained, let's say for those different languages, English, French, Italian, etc., you assign them to those memory arrays, and then you get a new text. And you don't know the text, you want to really classify it, you apply the same algorithm. So you encode the text, and now you assign that new vector, that query vector, to these memory arrays or these memory arrays. And what that really means, it means super quickly, in a very analog and efficient manner, you will get a current, and this current will tell you quickly about the best match and the Hamming distance. And therefore, you would know quickly that where and what is the best match, and therefore you would know the text to be classified to which language. And that's actually very straightforward. And if you think about it, you eliminate data movement because the classes will be trained offline, then stored once in the memory, and now at the runtime, you only calculate or you do the encoding and get the query vector, and then you send it to the memory, and the memory will respond back with the best match. So therefore, you don't do lots of data movement, you don't need to do expensive operations, and the Hamming distance done in an analog fashion, similarity calculated in an analog fashion, so therefore we can get the best match in a very fast, efficient manner. And that's lots of energy improvement coming from the algorithm itself, and on top of that, the way how we can do the computation of the hardware, and more importantly, the synergy between the in-memory operation, the logic in-memory Boolean function, and the underlying Boolean function in the hyperdimensional computing. And if you wonder, on top of what we have explained, why deep learning is not a good and not suitable for emerging technologies or beyond for human architectures, we should remember and keep in mind that if you really want to do emerging technology, which is by definition immature, and if you really combine it and couple it with beyond von Neumann architecture, where analog computing inherently immature and inaccurate, errors are inevitable. So you cannot really eliminate the errors, you cannot really get rid of them. So the only solution now we have is to make the algorithm or check the algorithm if it can survive with those errors. But deep learning is not good at all when it comes to errors. If you think about floating points, errors in the most significant bits can be catastrophic. Even for 8-bit integer, errors and the bit flips in the most significant bits can be easily catastrophic because of large error magnitude. So therefore, deep learning algorithms are not good to deal with errors. Even there's lots of attempts to do error-aware training, still in general, deep learning algorithms are sensitive to errors. On the other side, if you think about the hyperdimensional computing, we do all the computations in extremely large dimensions. We talk about 10,000 of bits. Even if error happens in some of those bits, and even if it happens in hundreds of those bits, it can be easily tolerated. And that is an example where an algorithm that can inherently tolerate error, and this is the best match within a hardware where inevitably suffers from errors. So therefore, again, that classical deep learning are not good and will not be suitable for emerging technologies and emerging architectures and beyond von Neumann, and therefore hyperdimensional computing as an example of non-traditional machine learning, or a machine learning that does the computations in a different and non-classical way becomes really key. And now the key is, if you have those errors and you know them, and even if your hyperdimensional computing can tolerate errors, you might ask yourself how much accuracy I would lose and whether I can even compensate that to keep and maintain my accuracy to remain the best. And that's what comes from that hardware, software co-design, or even technology algorithm co-optimization. And the idea is how we can ensure reliable hyperdimensional computing on top of all those errors that inevitably will happen and will come and will stem from the underlying hardware. We should remember that the ferroelectric is emerging technology. We have a new material, which is the ferroelectric material, which is not the material that we use to fabricate. So therefore, the material cannot be mature. So this is an example of design time variability due to the manufacturing process, also runtime variability due to temperature, and on top of that, inherent stochasticity in the material. And all of that, it only will cause us that whenever we do computations, we don't get this nice discharge current that I'm showing you here, but instead we will get a distribution. And these distributions, if you look at them here in this figure, you see that they start to really overlap with each other. And these overlap will interpret itself or manifest itself at the higher level as errors. And instead of you have, for instance, these Hamming distance calculations where you have from this confusion metric, you know, how it should be in the ideal case, you will start to get errors and probability of error. And therefore, when you do the computation of the hardware, there is a certain probability where you calculate the Hamming distance of I don't know, let's say 4-bit, but in reality it's 7-bit or vice versa. So there's a certain likelihood that you do and you interpret the current in a wrong way, where you calculate a different or incorrect Hamming distance. But no problem, we can go now to the hyperdimensional computing. We can include this probability of error, and then we can see that in this example, how the accuracy loss, it goes between or up to 1.6%. It's not too bad, which actually, due to the inherent robustness of HDC against errors. You see here that we have done the analysis for different voltages, because the lower the voltage, the better for power saving, for energy saving. But of course, this can come quickly at the cost of errors. So therefore, we can see here the trade-off that we can reduce the voltage and save lots of energy, but at the cost of higher probability of error, as well as, and as a result, higher inference accuracy loss. Or you can have it very robust, where the voltage is quite high, but the energy is very high. I want, before finishing, to also mention to you that in-memory computing and the whole concept of CAM and the XNOR operation, the logic in memory that I have just explained to you, it's not only can be done with emerging technologies, even existing technologies like CMOS and SRAM can also be used to realize CAM, content addition memory, and XNOR operation. However, it's more expensive when it comes to area. You remember we talked about Fero, it needs only 2 transistors to do the basic logic in memory operation. Here in the SRAM based, we need around 16 transistors, because we need actually 2 SRAMs and a couple of surrounding transistors to control it. We have done also the analysis for the in-memory SRAM, and we see here how in the ideal case the discharge rate will look like, and then how it looks like when we do the variability. And what we can observe quickly, that the overlap between those distributions is much less. And because the overlap is much less, we expect definitely lower probability of error. And if you wonder why the overlap is less, no surprise, because SRAM is really mature technology. It's a mature CMOS and robust technology compared to any emerging technology like Fero. We done the analysis again for the in-memory SRAM and the energy or the synergy, sorry, with the hyperdimensional computing. We see quickly here how the inference accuracy loss becomes much less, because the probability of error is much less. And we know that, and we remember that SRAM is very power hungry. So because it's a volatile memory that you have to keep it powered on the whole time. So therefore, voltage reduction becomes a key to save the energy. We done the analysis again for different voltages, and the trade-off is the same. Whenever we reduce the voltage, we get more errors from the underlying hardware, from the analog computing, and this higher error manifests itself again as a higher inference accuracy. But all in all, the inference accuracy that we are talking about is really up to 0.5% in this example. By the way, I forgot to mention, this analysis is done for 5 or 6 different classifications problems, like EEG signals, EEG brain signals, like the signal from audio classification, and the image classifications, as well as the traditional example that we started with, the language classification. This analysis is a summary and an average for 5 different data sets that has been analyzed or studied or investigated using binary HDC. And one interesting trade-off we can think about that you might say, yes, SRAM is more mature, that's true, and the inference accuracy is much less. However, SRAM is actually 16 transistors for the in-memory SRAM, and the Fero is only 2 transistors. So someone could wonder, why don't we trade off this area saving that I have in Fero and just do more replication, right? More replicas. And those more replicas will help me to do like kind of majority voting. And in other words, yes, Fero is less mature. However, Fero is very, very, very area efficient. And why don't I make use and exploit this area efficiency, or the gain in the area, or the save in the area, and just simply do more Hamming distance calculations. And if there are errors happening due to the immature technology, this will be compensated or this will be averaged somehow. And this we can see here that if we can do or exploit the area saving that's coming from the ferroelectric, we can actually reach the same accuracy of the SRAM. And if you wonder at the end, so what do we gain? We gain a lot because the ferro is non-volatile memory, which means it's not like SRAM where you have to power it on the whole time. There is lots of energy saving coming from the ferro. We have also applied the concept of the hardware software co-design for not only for the CAM array, but also we have applied for the traditional crossbar array without going into details, the same concept. And the key is, or the message is, if you really know how to model the errors that's happening from your underlying emerging technology, you would be really able to compensate that at the algorithm level, as we have seen in the previous examples. Finally, I want to really draw the attention of everyone that temperature is really the major concern when it comes to emerging technologies and analog computing. Temperature, when it fluctuates, it actually immediately represents itself as the fluctuations in the calculations, so in the signals. So therefore, if we have all the variability that's coming inherently and errors inherently coming from the underlying hardware, if we have temperature that keep fluctuating, which is inevitable, right? In our systems, the temperature is never constant. Therefore, we will get even more errors. However, the solution there is, and when it comes to those emerging beyond von Neumann hardware, we really need to monitor accurately the temperature at runtime. Because if we monitor the temperature at runtime and we understand the complete thermal map, we can actually mitigate the temperature fluctuation and we can keep the accuracy high. But the challenge is how we can really monitor and get the complete thermal map of the chip at runtime, knowing that we don't have sufficient thermal sensors on the chip. If you think about it nowadays, even in advanced processor chips, you have maybe one per core, let's say 4 thermal sensors or 8 maximum. But if you really want to get a very detailed thermal map, you really need a very detailed thermal sensor arrays, which is very costly and not possible in the currently, because simply it will occupy the silicon. And to solve this problem, we have actually fabricated for the first time a complete thermal sensor array on top of a very, very thin sheet. And this sheet, like a few micrometers, can be integrated on top of the silicon die under the heatsink. So these thermal sensors, this array, and in this example, it's 11 by 11, like 121 thermal sensors, can provide the operating system with a very detailed thermal map at runtime, in which we know precisely where the temperature, what's the temperature at runtime, and if there's any fluctuation to be compensated. We have also done recently even a higher dense thermal sensor array, and this is a world record currently that we achieved, 441 thermal sensors within 1 square centimeter. And the accuracy of those sensors are pretty much excellent compared to traditional on-chip silicon diode thermal sensors. And we can see how the printed thermal sensors can really capture precisely the temperature fluctuation. And again, such solution is beyond the algorithm. But what I want to draw the attention that when it comes to really beyond von Neumann and in-memory computing, errors are inevitable, and we need to compensate them not either first from the algorithm, but on top of that with also non-traditional ways at the system level where we can really monitor the source of the errors and try to compensate. This brings me almost to the end, and in-memory computing, indeed, there is a hope from it, but there is lots of hype, and errors are inevitable, and the reliability modeling is really key. And whenever we have accurate error models, those can be really used, and we need that we go to beyond the conventional deep learning algorithms, which are very power hungry, whereas in which algorithms like hyperdimensional computing becomes really key to realize such emerging technologies. And finally, and the most important thing, technology algorithm co-optimization is really the key in which we can bring hyperdimensional computing with all its key properties like robustness against errors together with the underlying hardware and the nice synergy with the in-memory computing. Before finishing, I would like, of course, to acknowledge our funding agencies, as well as our large network of collaborations, especially Global Foundries, Berkeley, and others, who are really supporting us from the underlying hardware and the emerging technologies, and we work closely with them. I believe we are on the brink of new era in AI hardware, and the promise really comes from looking to the novel emerging technologies and connecting deep device physics and beyond CMOS technology with computer science, where traditional or with novel algorithms like hyperdimensional computing, and bringing those two solutions together to realize ultra-efficient AI hardware for the next generations. This brings me to the end, and thank you very much.
Hussam, thank you very much for the great talk. Thank you.
Thank you.
Well, we have now time for questions. Maybe I can start with mine as a as a moderator. Listen, what I'm always wondering when I hear this hardware talks about kind of benefits of HDC on top of in-memory computing is this memory saving. But what about read-write operations? I mean, because I mean, search is important, you know, but the most often, what you use, you do encoding, like you know, compute engrams. So how this in-memory can help in this kind of computation?
So the in-memory, we should imagine that its job is mainly to store the classes. So once you have the classes offline, so they store the classes and they set. The encoding should happen in the traditional CMOS. So only when it comes to the similarity calculations, when we want to compare between the obtained vector query compared to the class, this is where the in-memory will happen. So therefore, we should not imagine that we do lots of writing to the in-memory, because then it's simply not working. It's it's slow, so it takes like 100 nanoseconds to microseconds. So the key is the in-memory job is really to hold and store the classes in the hardware. And everything when it comes to calculating and the encoding and the calculation, this will be done on the traditional CMOS. And the last step, when we start to do the Hamming distance calculation, the similarity check, this is where the in-memory computations comes into play.
All right. Okay, I see. Okay. So more questions from the audience?
Yeah, I have one. Gil Russell.
Yeah.
What's the duration?
Duration? What do you mean?
So how long does the persistence of the memory last?
Okay, the endurance, you mean? Or so the ferroelectric current, when it comes to the writing, it's around 1 microseconds, and when it comes to the read, it's in the area.
No. How long does the charge last on the device?
Okay, good. So this is subject to temperature, and it can go easily at this moment to 10 to the power 10 cycles, or 10 to the power. I think it can easily go to 10 years at this moment, or several years, I would say, but it depends on the temperature. If we go to the high temperature, the charges will leak quickly.
Right. The carbon fiber stuff is like 300 years now, so you're up against kind of that. Are you going to present at IEDM early next year?
We are, yeah, actually next week I will be at the IDM, and we are presenting a recent work that we have in the ferroelectric for back end of the line and the 3D integration next week.
Okay. Are you also familiar with self-organizing memory?
Self-organizing memories. To be honest, no. But that looks a fancy term, self-organizing memory. No, I'm not familiar with it.
Yeah, it's kind of complex, but you'll become very familiar with it in the future, I'm afraid. With some patents that have just showed up. Thank you. Very
Okay,
good
I'll
talk.
look about it. That seems interesting. Thanks.
All right, more questions? So let's see.
I have more.
Yeah,
Have
go.
you, what densities are you thinking about?
So density for the ferro.
Yeah,
So currently in the area of several megabytes already global foundries demonstrated in silicon. So the transistor size currently in the ferroelectric, it's in the technology of a 28 nanometer, 22 nanometer FD-SOI has been also demonstrated. So density in principle, it's the same density of 22 nanometer FD-SOI technology at this moment. But of course, when we talk about the memory, we don't really need a 6 transistor like the SRAM. So we mainly need a single transistor, but of course with some additional peripheries. So roughly speaking, in the area of a few megabyte or 2 megabyte, there is already a demonstration since a couple of years from global foundries.
so your application space is basically the edge.
Absolutely, absolutely the edge. And this is where something like HDC becomes interesting because we talk about a couple of classes or several classes that they are sitting on the chip and waiting for some queries to come. And this is where it's an interesting application compared to data, how to say, deep learning, we are by far more hungry or much larger.
You know, one of the things in Silicon Valley right now that's really very hot, but nobody, well, it's around the edges they're talking about, is AGI and the AGI solution. And what's interesting is nobody really knows how that's going to work out. But it appears that that HDC is part of the solution space that we see right now from our point of view. And how that runs on actual hardware is not been decided yet. Let's say that. And there's some discussion about the need for hardware now, and especially after we've seen happen with OpenAI and that imbroglio. And we're not sure that OpenAI is the first and the last of what we're going to see in this solution.
Right.
We expect more of a, what shall we say, an ensemble type of solution will probably be where it ends up. But the other one is that there's this old on the what we call magnetic RAM. Is the inability to determine whether or not the write has gone through. And
Right.
that is, how do you solve that?
Okay, so another problem just to mention in the MRAM that you cannot restore multiple bits. And I did not show or talk today that this Pharaoh has also the promise to store up to 3 bits, because in principle, you can really program it for different states. And now the single transistor is able to store 8 states, like 3 bits, which means, again, by far more density. Now, Pharaoh is quite robust. So if you really apply the correct voltage, you're pretty certain that you wrote the information correctly. So you don't really need to verify after the write, unless you do something like in between, like multi-state. But if you really rely on 0 and 1 and you apply very high voltage, like plus and minus 4, you are pretty certain that you really polarize the material into the correct direction and the correct level. So therefore, typically with Ferro, if we only target the binary 0 and 1, we are okay, and we don't really need to verify after the write. It only might be an issue if you want to be more, how to say, push the limit more, and then you want to really go to multi-states. And this is where you want to make sure if you have written state number 5 is really 5 or 7, and you want to really do some verification. But in general, this is not needed compared to other technologies.
Is any of this from the old Infineon effort in
FS23?
Yeah.
Yeah. So historically, which is really funny. So FS23, which is 20 years ago, has been researched a lot, and there's commercial products from Texas Instruments, Infineon, as you mentioned. But the problem there, it was like a ferroelectric capacitor connected to the transistor. And this has an inherent problem about scaling, so it remained large. So therefore, people gave up and stopped. But several years later, and there was, by the way, a company you mentioned, Infineon. There was a company here in Germany. I think it's called, not I think it's called Commanda. And Commanda was really researching a lot the high-K material and the hafnium to make the ferroelectric. And then after going to bankruptcy, the knowledge about the ferroelectricity and hafnium remained. Now, around 2010, people figure out how to integrate the ferroelectric in the gate of the transistor. So now imagine not anymore a capacitor, which is large and connected to the transistor. Now the ferroelectric is inside the transistor, and this allows scaling a lot. And because of the accumulated knowledge, and you mentioned Infineon, or let's say the other parties back then, because the accumulated knowledge over many years and collective knowledge, then the FEFET gained momentum and there was a very good progress in a relatively short time. But that's enabled the scaling. So to answer your question, is the same? Well, actually, it comes from the same root, which is a ferroelectric. However, the difference is the ferroelectric here inside the transistor, which enable scaling, which is very important. This is why we have very small transistors and ferro currently.
What's your terabytes per centimeter squared?
Sorry?
What's your terabytes per centimeter squared?
You
get that calculation ready?
I don't know the calculations, how to say, now in my mind, and I don't even remember. I read it straightforwardly. Of course, someone can really calculate it, but I don't remember I seen a direct number.
I'm trying to connect it with a 300 millimeter die, wafer rather.
Well, I mean,
I'm trying to say that you need to start thinking in roadmaps.
I'm pretty sure. Yeah, the people, the global founders and others, and TSMC also, I think they are working on it. There are multiple of those big players not already in the, in the interest of ferroelectric. And
what about stacking?
Sorry, the stacking?
Stacking, yeah. Can you take these transistors and stack them like flash memory?
Absolutely. This is, you asked me about the paper that we have in IDM next week. It's actually about stacking in a 3D manner, similar to the flash. So this is now a very good trend. And it's a lot about the back end of the line, ferroelectric, and going also in a 3D manner, like a nanowire, where you have multiple ferroelectric, like an NAND flash. And that will increase the density largely. So this is I would say the natural now evolution or the next step in the ferroelectric device, which is already happening the last 2 years.
Excellent.
But
Thank you.
I'm not aware of any companies demonstrated that. Of course, many people from labs demonstrated that from universities, but from companies, I have only seen traditional, I would say, memory devices, which are planar in the front of the line. And back to your point about edge computing, I really believe that, as you said, that HDC is within that space to be served. And more importantly, the promise is in the training. If you want to really think about training machine learning on the edge, any deep learning becomes almost infeasible, because inference might be, if you really reduce the size of the model and you build a nice accelerator, but training is really complex. You still need floating point and many complex stuff. But hyperdimensional computing, I would imagine an edge computing that does on edge or edge training, where HDC is the underlying algorithm, because it is possible compared to deep learning on edge I don't think it's possible at the first place. Easily, or let's say easily possible.
Well, we've gotten to the point where we don't call it training any longer. We call it teaching.
Okay.
Significant meaning.
Okay, sounds good.
Thank you very much. Very good presentation.
Thank you.
Okay, okay. So thank you once again, Hussam. So I see now we're approaching 1 hour, so I think it's time to wrap up. So thank you very much for coming once again.
My pleasure,
for
my pleasure.
a
Thank
talk.
you.
And thank you all for joining. So just to remind you, in 2 weeks from now, we have a talk from Yeseong Kim from South Korea. So please mark it in your calendars. But we end the webinar for now. So have a great week.
Thank you.
Thank you.